now we go back to the lecture notes on two random variables. So now we have two sample space, calligraphic x, calligraphic y. We have two random variables, x and y. Some important note, the ordered pair, bracket x comma y bracket, is not the same as x plus y. The bracket x comma y is the Cartesian product, x cross y, okay? So this is an ordered pair, it has two numbers. This is called Cartesian product, okay? This thing, the x plus y, is actually a subset of the x set plus y set. Let me be clear. Calligraphic x and calligraphic y are sets. X and y are random variable. That means they are numbers. So x plus y is a number. It gives us a single number, okay? It is not a pair. This is a pair. This is not a pair. They are already very different. Secondly, this is a Cartesian product. This is set addition. A set plus a set, this is called Minkowski sum, okay? So they are very different. Don't mix them up. So for example, I want to toss a two-sided die. That means I flip a coin and I have a four-sided die, y. Then the Cartesian product between set x and set y will be this set, Cartesian product with this set, and these are all the possible outcomes you can get on this sample space. But if we consider the Minkowski sum of set x and set y, then this is basically all the possible sum you can get. You can see that these two sets are different things. Now, the probability distribution of two random variables. So for example, we have x and y, and we have this table. So each box represents a particular joint probability. So for example, this means the probability when capital X takes the small x and capital Y takes the small y. Okay, this means the probability of an event x and y. Okay, so for example, capital X is 1 and capital Y is 1 is this box, which is 0.05. Capital X is 1, capital Y is 2 is this box, so 0.25, and so on. And recall the axiom of probability. The probability of sample space is 1. That means sum of all boxes must be 1. Okay? So always normalize the table such that the boxes is 1. Normalize means you take the sum of all the boxes, you get a number, and you divide all the boxes by this sum. Marginal probability. So for a joint probability, if we ignore one of the random variable, we call that marginal probability. So this means the probability of x ignoring y. So for example, we have this table. So what does this 0,3 means? This 0,3 means the probability of x give us 2. We ignore what is y. So that means I don't care whether y is 1 or 2. I just want the probability of x is 2. Then basically this number add together give us 0.3. What is this 0.7? It means the probability of seeing y is 2 regardless of whatever x give us. Okay? So basically it is three numbers added together. So this is the marginal probability. And how do you get marginal probability? You basically just sum the probability on the columns or rows. Okay? And this operation sum is actually sum rule. And make sure that the probability have to follow the free axiom. That is, all probability larger than 0, all probability sum together must be 1. Yeah, and make sure you use inclusion-exclusion principle if the intersection is non-empty set. Okay, if any of the axiom is violated, that means you're wrong. And lastly, we have the conditional probability. The conditional probability is saying that x given y. That means we know that y occur. What's the probability of x? The definition is joint divided by marginal, like this. Probability of x given y and the probability of x are two different things. They mean different things, okay? This is the marginal probability. This is the conditional probability. They are two different things. So here is an example. Suppose I have the sample space of x like this and a sample space of y like this. This is a table. And then I also have their marginal probability here. Then what's the conditional probability of x1 given y1? It will be the joint divided by marginal. It will be joint x1 y1 divided by marginal y1. So it will be x1 y1, this number, divided by y1, this number. So 0.05 divided by 0.3. That means 1 over 6. And if we have that the joint can be split into marginal, then we call x, y are statistically independent. Okay? This also implies that conditional is the same as marginal, having a meaning that knowing y tells nothing about x. That's exactly what independence means.